All right, we're getting pretty close to the end, guys. The handout that I've just given you, that's due on Thursday. And we're going to go through all the information you need, I think, to solve that one relatively quickly. And I also provided some pretty in-depth, step-by-step suggestions on how to do problem 16.9. Don't take that as an indication that it's super complicated. I just wanted to make it really explicit because of the quick turnaround on how to do that. As I mentioned via email, I've already looked at your project reports and graded them. You know, for the most part, I was really pleased at the level of detail you put into your calculations, and the drawings in general looked really great. So I hope it was a positive learning experience for you. I know that it's never fun to do work, but you know, you're here to learn the engineering design process, and I could tell from many of the reports that that was mission accomplished. So great job on that. If you have questions about the comments that I wrote, feel free to stop by during my office hours. I'd be happy to talk to you. On Thursday, our next class meeting, I'm going to talk a little bit more about the final exam. And so I'll tell you more about the format and the number of problems I expect to have on it and so on. So be sure to show up for Thursday, or at the very least watch the recording, because there's going to be some additional details about the final. So today we're starting on chapter 16, which is sewer design, and it is kind of like a blend of the first section of the course, which was closed conduit design, where we had water flowing in pressure through usually circular conduits, and open channel flow, which is what we've been doing recently, because now we're going to have open channel flow through enclosed pipes. It's just that the pipes aren't always flowing full. So the sanitary sewers and also storm sewers work with the same idea, that we're trying to convey wastewater towards some point of treatment or point of disposal. And generally it occurs in buried pipes that are flowing with open channel conditions, which means that even though it's a pipe, we're going to be using Manning's equation. And you'll remember way back we did a comparison of the Darcy-Weisbach equation and the Hazen-Williams and Manning didn't do so great in that head-to-head comparison because that was pressurized flow. But in this case, it's not pressurized flow. It's flow that's flowing partly full. And what we usually see along the streets are the manholes, which are spaced at an increment of between 100 to 300 meters, just as a location where crews can get in and inspect the pipes and clean them out occasionally. It's becoming more and more common for cities to use miniature cameras and robots to go down and inspect the pipes and try and limit the amount of sewage that seeps into the groundwater, or if the water table's high enough, to limit the amount of groundwater that's getting into the storm drains and into the sewage pipes. Service connections are the small lateral lines that connect homes and businesses to the larger main lines. And often it's a matter of policy or local code that service connections are owned by the homeowner. And so it's not necessarily the sewer company or the city that owns the pipe that goes to your house. And they do that intentionally so that when tree roots or whatever else may cause problems with your lateral connections, whenever there's an issue, then that's your responsibility to have someone come out and fix it. Because those are the most vulnerable pipes, are the ones that have the smallest diameters, that are at the shallowest slopes, and that are closest to vegetation, because they can become clogged and broken pretty easily. Occasionally, because we're flowing by gravity, the pipes have to be going downhill. We don't have the problem here in West Virginia, but there are a lot of places where the ground slope itself is relatively flat. And so that means that the sewer pipe is getting lower and lower and lower beneath grade, and so that occasionally they have to have some sort of a lifting station that will bring the sewer back up closer to the surface so that then it can start flowing downhill again, and that's called a pump station. Now, these sewer lines are going to be designed long in advance for the conditions that they need to meet. So the typical design life is 50 years, but here in most of Huntington, the sewer lines that we've got are still operational after they were put into place, in some cases, more than 100 years ago. And one of the reasons why we have such problematic flooding in Huntington is that they never conceived that we'd have the population that we do now. And they never expected that there would be so much paved area, because when you pave over the land, it reduces the ability of rainwater to infiltrate down into the soil. And so then that increases the amount of runoff there is. And so all of the water that's coming from sidewalks, from roof drains, from roadway surfaces, all of those, that land area, if you look down on a map where it used to be in the past plants and trees that would help promote infiltration into the soil, nowadays those are surfaces that don't allow any infiltration, so there's more water going into these collection networks than ever before. And so the pipe size was much too small. They weren't thinking in terms of what would be in the future. I guess, before cars were invented, people didn't think that paved roads would be as extensive as they are, but what we'll be looking at when we do design for sewers is populations in the future rather than the current population. There's a lot of variation in the way people use water. You've already looked at that, the curve where they're using a lot of water in the morning and then again in the evening because of the variation in human activity. So there's also a similar variation in when the water is going through sewer pipes. And so they have big peaks down at the sewer plant at night during the same times that people are using water for washing clothes, flushing toilets, taking showers, and so on. So there's a lot of daily flow variation. And the pipes have to be designed for the peak hour in the peak design condition some many years in the future. Now here's a couple of important terms that you should be acquainted with. Infiltration is when groundwater is seeping into drainage pipes because the pipe is either broken due to lots of years of aging or differential soil sediment that can cause cracks in concrete pipes. And inflow can be related to illegal connections where people are maybe connecting a basement drain to a stormwater or sewer network that they shouldn't be connecting a basement drain. It can be where there are small ventilation holes and manholes that's allowing in wet weather flows. Infiltration is relatively steady because that's mostly groundwater that's seeping in. And groundwater levels can fluctuate. The depth of the water table can vary when it's wet versus when it's dry. But it doesn't vary as dramatically as when there's wet weather. And so sometimes the flows in the middle of the night when there's not much human demand for water and therefore there's not much discharge for water, the overnight flow rates are usually what they call I and I, infiltration and inflow. And it's a really expensive problem because treating wastewater is an electricity intensive process. It consumes a lot of electricity. You'll learn more about why when you get into environmental engineering, but eliminating I&I can be a big cost savings for a municipality. So here is a sewer camera picture of some infiltration that's coming in due to a crack in a pipe. And this picture is showing a roof drain that's going straight down underground, which means that it's connected into some sort of a storm sewer. Hopefully it's connected to a storm sewer and not to a sanitary sewer. Because storm sewers, if it's just taking water from the roof, then it's probably okay to discharge that to a nearby creek without any sort of treatment. The roof isn't polluted. But if this is being discharged to the sanitary sewer, which is going through a really lengthy process of biological treatment, then that can add a lot of additional cost to the treatment, just the additional volume. Even though it's diluting the waste constituents a little bit, still the majority of the cost is related to moving the water from place to place and aerating the water and not so much related to the concentration of the pollutants in sewage. So both of these are bad things. It's just better if people allow rainwater to discharge over their yard to try and get the water to seep down into the soil with grass. Now, estimating how much water is going to go into a sewer is sometimes a matter of policy rather than a matter of actual engineering. in your project, you thought about how are people actually going to be using the water. But there are a lot of ordinances in place that dictate for engineers what assumptions you have to make for sizing sewers. And I suppose that's because when there weren't rules in place, people were pushing to the extreme and undersizing the sewers with arguments that were favorable for them. You know, a developer who's putting a new subdivision in wants to put in the smallest sewer possible. And so rules like that are quoted here are put in place just to make sure that the pipes are large enough. And so you see there's a huge variation. In Milwaukee, for instance, they're saying that per person you should allocate 1,000 liters per day of capacity in the sewers. That's how much wastewater we expect to be generated in Milwaukee. Lots of toilet flushing in Wisconsin, supposedly. Plus, they say that you should also allocate a little bit of extra capacity for possible inflow and infiltration. But if you contrast that with Berkeley, California, then 350 liters per person per day. And so part of the variation can be related to how well maintained a collection network is. It can be related to climate factors, where maybe they're expecting there to be a combined sewer in Milwaukee, which is that there would be a lot of stormwater influence in a sanitary sewer. But could be, yeah, Berkeley, fewer showers. You know, that's as likely as anything. But the point is, when you're doing sewer design, you need to be acquainted with the local ordinances, and sometimes they diverge from reason and diverge from engineering logic. So you'll have to know in an area what you expect the future population density to be, and that can be based on zoning. And once you know the population density and the local ordinance, then you can start to generate stormwater flows. And so here are some typical population densities for different types of land use. You know, where you have a multi-story apartments, really congested living conditions like in an urban area, then you could have up to 2,500 people per hectare and even more. In fact, I think in Hong Kong they have up to 10,000 people per hectare. No, in a lot of cases they're just local codes that were developed by their local building inspectors, and there's usually sewer agencies. You know, Huntington has, the sewer authority in Huntington is the Huntington Sanitary Board. And there are state laws that influence the sanitary board, but they can have their own regulations that are even more strict than state regulations. Commercial and industrial connections are somehow similar in a way, just where there can be a huge amount of variation in what the expectations are, how much wastewater you should be prepared to accept in a sewer per area. And so you'll see here in Santa Monica, California, they're saying expect 91,000 liters per day per hectare of commercial space, and then it can be much lower in other places. And so you just have to be familiar with what the requirements are, and the exception to this is that sometimes industrial facilities that have particularly dangerous discharges may have their own on-site treatment. And that can include food processing plants, where you wouldn't think of a food processing plant as being dangerous. But because food has a really high oxygen requirement, if you have discharges from a food processing plant going into a sewer, then that can cause a lot of strain on the biological treatment that's downstream of that. And so it may be required for paper mills, sewer, food processing plants. Sometimes metal processing and heavy industries will have their own treatment system to try and prevent the introduction of toxic materials and heavy metals from getting into the domestic wastewater treatment systems. So in a case where you're designing a facility that's going to have its own treatment system, then that is one situation where maybe you'd be permitted to deviate from the local code expectations.
How difficult would it be to go in and edit a sewer system like somebody from Michigan when it floods?
Yeah.
I mean, I've heard people saying it's cheaper to just build it.
Than to replace the sewer pipes? Probably not that expensive, but it's really, I don't think it'll ever get done. So his point is, is Huntington's undersized sewer network, is it ever going to be fixed? I don't expect to see it ever fixed. There's just simply not enough money in the United States for like every community to get some grant from the federal government to fix that. And on a local basis, nobody wants to pay the taxes for something as boring as like increased pipe sizes in the sewer. I mean, it annoys people a couple times a year, right? But it doesn't annoy them enough that they want to spend the money on that. 3 million? Yeah, that money's already long gone. It's spoken for, right? They probably wouldn't give us the check if we'd said we were going to buy new sewer pipes with it. Yeah. Good question. Now, infiltration and inflow, remember those flows that are related to crack pipes and wet weather. Well, having an effective inspection system, making sure that the pipes are laid out on good subgrade base, good workmanship, and making sure that they are inspected regularly and trying to repair the crack sections will decrease how much I&I there is. But in order to do calculations related to this, there have been just these empirical studies that have related the relationship between the peak flow rate you can expect from a city relative to the average flow rate as a function of population. So this is a little bit different from the curve that we had for the project. Remember, for the project, I think the peak hour was, what was the factor? 4.25 times the average day. Well, this is saying that if you have a small town, then you're going to have more of a peak compared to the average. So the fact that this is in the denominator says that if you have a small town, you can expect more flashy peaks in the flow rate compared to if you have a big city. Anybody want to speculate on why that might be the case? Why the ratio of peak flow to average flow is going to be more extreme for small towns than for large towns? Okay. All right, so you guys are hitting on an important factor. So part of it is related to, in a small town, maybe everyone works at the same employer. Everybody's working at the local mill or the local factory. And so in a large city, there's, the city that never sleeps. People are going to be showering and washing dishes and flushing toilets at all hours of the night. So it's partly related to human behavior. And it's also partly due to the geographic diversity. So that if you have the water all going towards some central sewer plant in a big city, it takes a long time to travel there. And that dissipates the peaks. Where if we think about a large city, like a big city like Columbus, Ohio, then the sewage that's generated on the far northern edge of Columbus, it takes several hours to travel down to the treatment plant, compared to a smaller town where if they have a centralized wastewater collection network, the travel time is going to be less. And so I think you get the idea that the spatial distribution of where the wastewater is being generated helps to limit the difference between the peak and the average if you have a big population. And so it's a similar thing here where the ratio of the minimum to the average is going to be more variation for small towns than for big cities. So what is the time? We've got a lot to get through today. We might skip over this example. We'll come back to this example if we've got some extra time at the end of class, because this is just kind of plugging numbers into the equation, and we've got bigger fish to fry today. So the bigger fish we've got to fry is watching videos, of course, watching YouTube videos. All right, dim the lights here. All right. lights in here. There we go. That's better. Like I said before, we're going to be designing sewers for a condition that will almost never exist. We want to design the sewers so they're big enough to carry all the flow that there's going to be when it's raining, 50 years from now, when the population is totally built out. So they don't often flow at full capacity, but sometimes they do. Let's look at one of those sometimes, because it's pretty exciting. All right, so it's raining. You can tell by the reflection. It's raining, right? Something's about to happen. Hello. Wait for it, wait for it. There's someone in there. Yeah. Yeah. Ran into the manhole. The manhole cover just blew off. Used to be there. Yeah, it's his truck down the tubes. It looks like a truck. All right, so what happened was that the pipe became surcharged, as it's called. That means that it's supposed to be gravity flow, but this may be a low-lying section of the pipe network, and there was so much water coming into other locations that it pressurized a section of the network. Oh, get out of the way, man, get out of the way! Run away! That's what's going through his mind. These guys are still driving at full speed. They couldn't care less. So, lightning, flooding. That's a beautiful video, isn't it? It's one of my favorites. Yeah. All right. Well, we could watch sewer explosions all day long. Let's do the calculations, though. All right. So the geometry is a little bit complicated. The geometry of a partially full circular pipe. Now, here in this sketch, we're calling the depth of water H. I think some of the other formulas that we've got, it's called Y, and I know that won't throw you off too badly. It just basically means the depth of flow as a function of the overall pipe diameter D. Now, theta here is the angle that the water surface makes relative to this center of the pipe. And so if the pipe is half full, what is theta in radians? If the pipe is half full, pi radians, right. So what we can do is if we know the angle, then we can calculate the depth of flow, the cross-sectional area, the wetted perimeter, and so on. If we combine all of this with Manning's equation, then Manning's equation transforms into this. And so this is Manning's equation. If you know the angle, theta, which always needs to be radians, so if you know the angle that the water makes, and you have the end value of the pipe, and the diameter of the pipe, and the slope, then you can solve for Q. All of this is equal to 0. And so you can solve for the unknown flow rate if that's the unknown thing. So that seems pretty tricky, but unfortunately, that's not the end of it. Because the N values that we're used to using are N values that are developed for pipes that are full. And so the N value varies as a function of depth. It's not constant. So we have to make adjustments for the N values. There are a couple of ways to handle it. You can either compute the flow rate assuming that the pipe is full and then do a correction with a nomograph I'm going to show you in a minute and a separate correction for the N value. But what we'll do is a procedure that kind of iteratively handles everything. So you're given a flow rate and a pipe slope, an N value, a full, the material N value roughness factor for when the pipe is full and diameter. And in a lot of these problems, you'll have to solve for the theta in order to find the depth of flow. Now here's that graph that I was mentioning. And what this shows, first of all, the first curve I want to show you is this one. And this curve is the ratio of the flow capacity of the pipe compared to when the pipe is full. So if you follow it, down here is the axis. It says Q to Q full. It's a ratio. Here's 1.0. Now it makes sense that when the depth of flow is equal to the diameter, that it's 1.0. But this is weird. Look at how it's to the right of the 1.0. So what that says is actually you can get more flow through a pipe if it's almost full than if it's totally full. I wish I had a marker. How about that? All right. So what that says is that you're better off having this much water in the pipe than having it all the way full. Anybody want to speculate on why you get more capacity through the pipe if it's almost to the top than if it's all the way to the top? Added friction, right. All of this additional friction length at the top is less beneficial than the additional cross-sectional area that the water can go through. And so that's why for a brief period it's above 1.0. But usually having the pipe not all the way full means that you're not going to get the full capacity. So for example, if the flow depth, if the ratio of Y to D is 80%, 0.8, we follow this over, that means that you'll get about 87% of the flow capacity. And so it's a circular pipe, and so that means that there's some nonlinearities here, and that's what we can see from the curve. So there's a similar expression of the velocity of flow compared to the velocity when the pipe is full, and that's related to how much of the flow area is away from one of these frictional surfaces to give you the average velocity. All right, and then the ratio of the Manning's N to the N value when it's full. We read that off of the top here, and you'll notice that the best you can do here is 1.0, the N value to N full. So if the pipe is all the way full, then you have an N value the same as N full, but otherwise the N value is larger if it's not all the way full. And we'll look at some calculations that kind of illustrate the implications of that. Let's say we have a 24-inch diameter concrete pipe. Now, this concrete, when the water is flowing through the concrete pipe all the way full, then the N value is 0.013. So as a flow depth of 9 inches, that's Y. The slope is 0.5%, and when we put that into Manning's equation, remember we need to treat that as 0.005. We want to know what's the flow rate that's going through this pipe. If it's 24-inch diameter, but it's only got 9 inches of depth. So the process that you're going to go through here is, first of all, find the angle of the flow. And here's the formula that will allow you to calculate the angle if you know the Y flow depth and D. So notice that the function here is the inverse cosine. On my calculator, that's abbreviated ACOS. I don't know, on the Casios, is there an ACOS function if you push the function button? Cosine to the negative 1? All right. So that's what we're doing. Cosine to the negative 1 of 1 minus 2 times the ratio of flow to diameter, all that times 2. So that'll give you the angle. Once you know the angle, then you can use this formula to get the cross-sectional area, this formula to get the wetted perimeter. Then you use the figure to find out what is going to be the N value that you should put into Manning's equation, because you know the Y to D, and so you can go over here and find the correct N value, the ratio of N to N full, and then finally substitute everything into Manning's. All right, so I'm going to pause the recording, give you some time to calculate. I'll be circulating around with the answer. All right, so we know that the ratio of Y to D is 0.375, right? So if it's 0.375, then this would be 0.3, 0.375 is up here. So we're going to go over and find the curve for n to n full, and then down. And so that is, I said, oh, sorry, up, not down. Up. All right, so 0.375 up. That's clearly 1.28. Very clearly 1.28. So what that means is that the n value should be 1.28 times n full. So what we substitute into Magning's equation is going to be 0.013 times 1.28, or whatever you read that to be. So it'll be straight up from here. All right. So the n value, I got 0.01664. That's a little optimistic on the precision. So the angle, 2.636 radians. Everybody get that for the angle? Close, okay. So then we find the cross-sectional area, and it's 1.076 feet. And then the wetted perimeter, 2.636 feet. And then substitute all of that into the flow rate with the adjusted n value, and you should get 3.75 cubic feet per second. Now, there is a Q to Q full function as well. So we could calculate the full flow, the full depth flow rate, and then find the Q to Q full based on the Y to D. So that would be another approach. Let me bring this back up. So any questions on this example? Q full? Well, if we'd calculated Q full, it should be 4.8 cubic feet per second. Well, that's based on the n full, actually, just if it's the n full. So if you wanted to calculate the Q full, then what we would do is we would say that the area is based on the full diameter of 24 inches, and the wetted perimeter is also based on the full flow conditions. So we'd have to substitute in, assuming that the water's all the way to the top. All right, so that's the analysis of finding out for a certain flow depth what is the flow rate. But the next step beyond the analysis is design, making sure that the pipe is large enough to accommodate the flows that you expect to see. Before we move on to the design, is there any lingering questions on this example? Mm-hmm. Yep. And then this is the n to n full. Yeah. The final answer is 3.75 cubic feet per second. So 3.75. So we've got 1.49, which is the units conversion for VG units. The area, 1.076 square feet to the 5/3 power. We're putting in the n value, that's the corrected n value based on it not being full, so 0.01664. Wetted perimeter, and then the slope changing from percent into fractional format. 3.75 cubic feet per second. I mean, it can be a little bit different depending on how you read the n to n full ratio off the top part of that nomograph. This is the flow rate that we're going to see. This is not Q full. This is the flow rate that we're going to see for the conditions that are described. To calculate Q full, you would use the 0.013 and you'd calculate the area of an entire circle and the wetted perimeter for the entire circle, and then you could get your Q full and you could multiply it by this ratio, the Q to Q full, and it would match. You don't seem to comprehend. Okay? So we don't really care about Q full. We want to know what's the flow rate under these conditions. So the flow rate under these conditions, when you've only got 9 inches of water going through a 24-inch pipe, that's the 3.75. So we went through the procedure and found that. The alternate procedure, another way to find it, would be to assume that you have the full flow, and then once you have Q full, then you could find the ratio of Q to Q full based on the ratio of Y to D. So then we'd go, the 0.375 down from there, it looks like it's about 0.2. And so this flow rate that we found of 3.75 cubic feet per second, that's about 20% of the flow rate that would be there if the flow was all the way to the top of the 24 inches. Yeah? You said, what if you don't know the flow depth? Mm-hmm. So in this hypothetical that you're describing, what are we trying to find? Okay. If you don't know the depth of flow, then you can't find the flow rate.
So they would always measure, but they would never arbitrarily guess.
I may not follow you. So they may make some assumptions when they're sizing the pipe, but you can't say how much water is going through the pipe without knowing something about the water depth that's there. Yeah. So let's do that design now. Here's Manning's equation if we rearrange it in terms of D. And so this is the geometry where we've got a circular pipe. And so we're going to substitute in the geometry for the area in terms of D, the wetted perimeter in terms of D, and then this factor here, X, that's related to whether you're working with traditional units where it's 1.49, or if it's SI units, then it'll just be 1. So you know some given flow rate. The flow rate is given Q, and you're trying to find out how big should the pipe be. And by the way, these units will be either in meters or in feet. So let's say that you find that the pipe needs to be 11 inches in diameter. Well, there aren't 11-inch diameter pipes available for purchase. And so you'd have to size up and buy the 12-inch diameter pipe. And so you'd round up to the nearest actual available size, and then you'd have to sort of evaluate what are the conditions at the maximum flow rate. And so it's similar to the process that we just went through. You'd have to find out what is the angle for the conditions, and then find out the flow depth given that maximum flow rate. And then you also need to consider what's happening during the minimum flow conditions. And the reason why minimum flow conditions are important is that most of the time you have the minimum flow condition, and the velocity can be moving so slowly that sediment particles will settle to the bottom of the pipe. And there can be an accumulation and deposits of things like grit, sand, other things that go through sewage. So you want there to occasionally be flows that can cleanse out deposits. And so a typical rule of thumb is that the velocity at minimum flow conditions should be greater than 2 feet per second to try and prevent problematic sedimentation. So here's a picture of a nice clean pipe that the minimum guideline is being honored, and then here's a clogged pipe just to illustrate the kind of deposition that can occur when you've got flows that are too low. All right, so to go through this process, we're going to use a template file that I've uploaded to MU Online. You should be able to download it. It's just right at the main page of the site. It's an Excel file. And we're going to go through the process of designing and analyzing a concrete sewer pipe to carry a maximum of 2.5 cubic feet per second, and the slope is 0.75%. Now here's the minimum flow rate. We're going to have to check and see if the minimum velocity of 2 feet per second is available at that minimum flow rate. We're going to use our N full of 0.013 and in this case neglect N variation with depth. I think actually in my updated N value. Yeah, for this example we are going to neglect N variation with depth. On the handout for the homework though, I've described a process that you should go through where you have to make some iterative changes to not neglect that. So we'll do one and then the other. All right, so everybody have that template file. It should look like this. All right, everybody's got it. All right, so the first thing is these are traditional units, and so the factor that we're going to use for x is 1.49. Okay, our maximum flow rate from the problem description is 2.5 cubic feet per second. And then the minimum flow rate is going to be 0.45 cubic feet per second. And the slope is 0.75 divided by 100. Okay, so 0.0075. And then the N value, 0.013. So here's the formula. This is just Manning's equation rearranged to solve for the diameter assuming circular flow. So if the water was, if we had the perfect size pipe to accommodate the flow with no excess headroom, this is going to tell us what that diameter would be. And we're going to solve for it in feet to begin with. So 1.55 times Q max times the N value divided by the X value. I need to anchor that reference to the N value. All right, times the slope to the 1/2. All right, and then all of that is to the 3/8 power. Thanks. All right. Okay, so it tells us that if we could, what we'd want to do is go out and buy a pipe that's 0.924 feet in diameter, which is 11.09 inches. And they don't make pipes that size. We're going to have to go to the nearest actual available pipe size, which is a 12-inch pipe. And so we're going to use an actual diameter of 1 foot. So now what we have to do is we have to say if it's 1 feet in diameter, what's the actual, how deep is the flow through there? And the process that I've got set up here is, we're going to be starting with some guess value of what the angle is, and then solve for the normal depth at that guess. Right-hand side. So this is rearranging Manning's equation. We're going to have the right-hand side, which is N times Q divided by X times S to the 1/2, and then the left-hand side is going to be the area to the 5/3, the wetted perimeter to the 2/3. Now, the area is going to be based on this formula, which is dependent on theta. The wetted perimeter is based on this formula, which is dependent on theta. So we're going to start with just some guess. Let's say maybe that the angle is 1 radian to start with. And so having that allows us to calculate what the cross-sectional area would be. All right, so angle minus the sine of the angle. And this is the one instance where we're actually kind of fortunate that Excel assumes angles are in radians, right? Normally we have to convert it to degrees, but this time we don't. Okay. All right, and now the wetted perimeter is the angle times the diameter divided by 2. So this diameter divided by 2. So then the left-hand side of this equation is going to be the area to the power of 5/3 divided by the wetted perimeter to the power of 2/3. Oh yeah, you're right. Thanks for noticing that. I do. Yep, you're absolutely right. So multiplied by diameter squared divided by 8. Okay. So as I typed it earlier, I had the theta minus the sine theta, but not the diameter squared divided by 8. Okay. And then here, for the right-hand side, we've got the n value, which my reference to it is there, n times q max divided by x times the square root of s, so s to the 1/2 power. Q max. So the left-hand side and the right-hand side right now don't match. The difference between them is just one minus the other. You can probably guess why we're calculating the difference, because what we want to do is we want the difference to go down to 0. So we're going to keep changing the angle in radians until the difference is equal to 0. Do that with goal seek. Set the difference equal to 0 by changing the angle. And so we're going to solve until we get the angle in radians. All right. Now you could put this into your calculator. You know, you could define A in terms of theta. You could define P in terms of theta. And everything was already known on the right-hand side of that equation. So I'd be interested to know if that's something that Casio can handle. I don't know. A couple hours? Oh, it wouldn't take hours, but it wouldn't be as quick as Excel. Maybe less tedious to set up. I don't know. Let me pause this for a second. All right, so we know what the angle is going to be, so now we can substitute this formula in to find for the actual flow depth. So it's going to be the diameter that we're building the pipe to. So we're actually going with a 1-foot diameter pipe divided by 2 times 1 minus cosine of the angle divided by 2. Okay, so the flow depth is going to be 0.681 feet. Now, under minimum conditions, we want to do a similar thing, except for now find out what's the flow depth when we have minimum conditions. That was this 0.45 cubic feet per second. So the right-hand side meaning of this rearranged Manning's equation is going to be the n value times the flow rate minimum, 0.45, divided by the x, 1.49, divided by the slope to the 1/2 power. Okay, and we'll put in some guess value for the angle, maybe 1 radian, and then, let's see, can I copy and paste that formula? Let me anchor the reference to D14, and then I think I'll be able to. What about the wetted perimeter? So I'll just copy and paste that. So the left-hand side, copy the formula, paste it, the difference. So right-hand side minus the left-hand side. Okay, goal seek difference to 0 by changing the angle. Okay, so we know the velocity. We can calculate it. The minimum flow rate is just going to be the minimum flow rate divided by the area of flow at the minimum flow rate. So it's going to be 2.85 feet per second. You remember that the limit is that 2 feet per second or more should be seen at the minimum flow rate to prevent sedimentation. So actually, if you've got a pipe that's too big, then that can bring your minimum cleansing velocity below the 2 feet per second. And so sometimes it's a problem. People think that just make the pipe bigger is always the solution to every problem. And you need to have the pipe large enough to handle the maximum flow. But if it's so large, then think about what actually the flow depth is going to look like. Oh, this is a permanent marker. In for a penny, in for a pound, right? So, so if you've got just a little bit of flow and it's really close to the bottom depth there, you'd see that most of the flow is right in contact with the surface where the friction is being applied. And so you're going to have a really low velocity. Whereas if we had a smaller pipe, then it would have been more full and the velocity would have been faster. So you want to have the pipe be large enough, but not excessively large. Somebody will clean it up. I'm sure like an alcohol or acetone or something. All right. Yes?
Could we just increase the slope?
We could increase the slope and that would increase the velocity, but that's not something we usually have control over because these pipes are laid out at the slope that corresponds roughly to the ground slope. And so, you know, if we're starting in Beverly Hills of Huntington and the water's going to end up at the sewer plant next to the river, then there's just only so much elevation difference that we've got. Yeah. All right. One last thing we're going to talk about today is hydrogen sulfide. And it's a dangerous gas that can actually cause people to die. And it does. Every year, people die of hydrogen sulfide. And if you've ever driven by people doing sewer maintenance, look carefully next time you do. They are really, I mean, if they're doing things right, they're really cautious. The guy who's going down will have a tether on him. They'll have a hydrogen sulfide detector. There's someone at the surface ready to pull the guy out if he becomes unresponsive because of this gas. When you have anaerobic conditions, meaning that the water that's flowing through the pipe runs out of oxygen, then bacteria will start to break down sulfur and form hydrogen sulfide. So at first it smells bad, but then it overwhelms your ability to smell it. And very low concentrations can be fatal. So why we care about it in terms of hydraulic design is that another one of the reasons we have to ensure that the velocity is high is that higher flow velocities will help to prevent hydrogen sulfide, because hydrogen sulfide forms when the water is kind of stagnant, when there isn't any mixing of air and water together. We don't really control the temperature. Increased temperatures also increase the formation of hydrogen sulfide, so we can't adjust that, at least not really economically. We could refrigerate the sewage, but people don't do that. But they are paying attention to the potential for hydrogen sulfide, and there's an empirical equation that's been developed to kind of allow you to predict whether hydrogen sulfide is likely to form. It's a sulfide potential factor, Z. It's just an empirical approach that takes into account the wetted perimeter, the top width of the water surface depending on the flow shape, the slope of the channel, the flow rate Q. So we're getting pretty close to the end of class time, so I wanted to show you this example. We won't have time to go through the calculations, but I will show you the calculations. If you calculate a Z number and it's below 5,000, then that means that hydrogen sulfide probably won't occur. And these are the Z conditions that are typical if you have a pretty good slope. You know, if you've got a good slope, or if you don't have this kind of an extreme where you've got a really oversized pipe that's super shallow flow, that's going to really slow things down. So that's what this ratio of the perimeter to the top width is kind of taking into account, is the flow geometry. And it's an idea of what the velocity is going to be as the water moves through. Now this EBOD is an environmental factor related to something called BOD, which is biochemical oxygen demand. And that's how much pollution is in the wastewater. One of the ways that they measure pollution is how much oxygen would be required for bacteria to break down all of the organic material in the wastewater. And so the E means effective BOD, which is where we're just adjusting the BOD as a function of temperature. And warmer weather promotes hydrogen sulfide formation. And so we'll take the temperature in Celsius, minus 20, and so 1.07 to the power of T minus 20, multiplying that by BOD, will tell you the effective BOD. So if we had more time, this is the example that we'd work, and I'm going to show you the solution to this in just a minute. We've got a sewer where we know the diameter and how much flow is going to go through here, the temperature of the wastewater and the slope. So the first thing we'd need to do is kind of just a geometry analysis, because the EBOD formula needs to know the wetted perimeter and the top width. And so once we do that, once we have those parameters, then we're going to look at, for this BOD of 350 milligrams per liter, what's the effective BOD, and then what does that all mean relative to this chart of Z potential? How likely is it that hydrogen sulfide is going to form? All right, so that's not it. So here's what we would do for that one. We would start off by for the diameter that's given, calculate the angle in radians. So this is that formula I showed you earlier, which is just Manning's equation rearranged to solve for the angle. So we know the flow rate Q, we know an N value, the slope, and so on. So for an angle in radians, we can find the wetted perimeter and the top width B, and we can find the depth of flow. Here it's called H, but in the formula we were working earlier, that was just Y. So we've got all these geometric parameters, and we find the effective BOD based on the temperature. If it's 350 milligrams per liter at normal 20-degree temperature, then the fact that we're at 33 instead of 20 is the equivalent of having a BOD at 843. So a really highly concentrated wastewater. So we put that into the empirical equation to solve for Z, and we get 7373, which is in the middle range, which is BOD formation is possible. It's not guaranteed, but it is possible. So we'd need to be cautious as people were maintaining that section of the sewer. Or if possible, rearrange the geometry of the sewer to make it so that the P to B is lower. All right, so remember your final homework assignment is due Thursday. And if you've got questions, feel free to stop by my office during office hours, and we're going to talk about the final exam on Thursday. So encourage your classmates who haven't been here in a while to maybe at least pay a visit on Thursday. All right. Take care.